Okay, we were discussing with this with these hyperplanes in SVMs, and in the last lecture I mentioned that we would be interested in maximizing the amount of separation or marginalizing this separation distance, which is linked inversely to the norm of the optimum hyperplane, norm of the vector W, right. Now, maximizing the distance of separation is equivalent to minimizing the norm on W, right. That is where we started off with. Now, let us formulate the setup of the solution to the SVM problem for linearly separable patterns through an optimization framework. Okay. So, what we are given here is this set F that comprises of pairs xi di, I equals 1 to n, we have n examples, and we want to find an optimal hyperplane subject to the constraints di times W transpose xi plus b is greater than or equal to 1 for I equals 1 through n. So, what this means, when W transpose xi plus b is greater than 1, you treat this as di to be 1, and if it is less than, you have di to be minus 1. So, therefore, a plus 1 and when W transpose xi plus b is negative, right, when W transpose xi plus b is negative, di is minus 1, and when W transpose xi plus b is positive, then di equals plus 1. So, you have a plus 1 times some positive quantity, and then you have a minus 1 times some positive quantity here. Now, that is the meaning of this this equation here, and we need to choose a weight vector W that minimizes the cost phi of omega, phi of W here, that minimizes the cost phi of W, which is 1/2 W transpose W. Right, you can clearly see why I have this half, because when I take some derivative, this 2 should cancel out, particularly when I have a quadratic cost. This is a quadratic function, it is convex, and the constraints are linear in W. Okay, so these are my constraints, right. Di times W transpose xi plus b is greater than or equal to 1 for all examples I equals 1 to n. Let us set up the Lagrangian. So, the overall cost j, or my Lagrangian, is given by 1/2 W transpose W minus, for every constraint I have a Lagrange multiplier, and since they are inequality constraints, I have to stick a negative sign before the constraint, and we saw that reason when we looked into the optimization basics, right, basics of constraint optimization. So, j, which is a function of the weight vector, this is the bias, and this is a vector which comprises of all Lagrange multipliers for each constraint. And I can write it in this form: j of vector W comma b comma vector alpha equals 1/2 W transpose W minus the summation over all these constraints that are scaled by their appropriate Lagrange multipliers. So, it is summation I equals 1 to capital N alpha I times di times W transpose xi plus b minus 1. Now, for my optimality constraints, optimality conditions, I need to take the derivative of this Lagrangian function with respect to the vector W, set that equal to 0, then take the partial derivative of the Lagrangian with respect to the bias, set that equal to 0, and then trivially, of course, when I take the gradient of this derivative of this Lagrangian with respect to alpha I should get back the constraint. So, this is straightforward. So, conditions 1 and 2 are important, condition 3 is trivial because you have to get back the constraint. Now, let us go further. We evaluate the partial derivatives. So, for condition 1, which is d bar j upon d bar w equal to 0, if we solve this, it is pretty straightforward. You can do simple matrix differentiation with respect to a vector, and following the rules of matrix calculus. W happens to be summation I equals 1 to capital N alpha I di times this vector xi. That is equation 1. Condition 2 gives me, when I take the derivative with respect to the bias, I just have to focus on the term, on the coefficients that stick before b, and they are alpha I and di, and what I land up with a summation I equals 1 to capital N alpha I di equals to 0, right. That is my condition 2. Now, since I am solving a convex optimization problem, because of the nature of the setup, the solution is unique, right. So, if I solve for these conditions subject to the constraints, then I am home for good. One important note is the following, and I will leave this intentionally as part of the homework exercise. It is important to note that at the saddle point, for each Lagrange multiplier alpha I, this quantity alpha I times di times W transpose xi plus b minus 1, this quantity is equal to 0 for all I equals 1 to n and alpha I not equal to 0, right. Alpha I can be greater than or equal to 0, and for alpha I not equal to 0, what boils down is this condition d suffix I times W transpose xi plus b equals 1. So, I want you to ponder about this condition. In general, in optimization problems, we are interested in the notion of primal and dual problem. For example, if I am maximizing some quantity subject to some constraints, I can formulate the dual problem by negating the sign in the objective, and I am minimizing something subject to some constraints. Maximizing something is minimizing negation of that subject to some constraints, and whatever optimality conditions I derive in the primal problem by taking the derivative of the Lagrangian with respect to the parameters, I can plug that into an equivalent form and I can land up with the dual problem, and the dual problem also has the corresponding optimal values, right. For non convex problems you can have this gap between the primal problem and the dual problem, and you want to reduce this gap through your optimization techniques, but this gap is basically 0 for convex problems. So, in one case, particularly for this SVM problem, for the primal problem we are interested in solving this optimum weight W optimum, whereas in the case of the dual problem it boils down to finding out the derivative, the condition with respect to an alternative variable by setting the derivative of the dual problem with respect to that alternative variable to 0 and then trying to solve this problem. I will not discuss more details into primal and dual problems because this is part of any optimization course, but once we formulate the problem in the primal form, I will just invoke the dual form, and from there we begin our journey in our discussion through the SVM section here. Okay. So, we formulate this Lagrangian like this: J of W comma B comma alpha, where W and alpha are vectors, is given by this quantity. So, what I have done is I have expanded the summation I equals 1 to n over the Lagrange multiplier times the constraint in this form. So, this boils down to 4 terms. One is half W transpose W, which is basically our objective, and these terms here, which is 2, 3 and 4, are basically from the constraints. So, this is basically by expanding the primal problem. So, from our optimality conditions, because I looked into the gradient of the Lagrangian with respect to the bias, and that I set this equal to 0, from that condition I had sigma I equals 1 to n alpha I di equal to 0. So, therefore, term 3 just vanishes out. So, all I have is this first term here, which is basically my objective, terms 2 and 4, which I can simplify in a certain form. Now, I compute W transpose W. So, basically I replace W by summation I equals 1 to n alpha I di times xi. Alpha I and di are scalars, xi is this vector. So, therefore, W transpose W is this from condition 1 by computing day bar j upon day bar W. Okay. Now, W transpose W is basically summation I equals 1 to n summation j equals 1 to n alpha I di alpha j dj xi transposed xj. This is straightforward. I just plug in W transpose and then I expand this out, and I have to have two different variables I and j. Now, these alpha i's are non-negative, that is they are greater than or equal to 0, and I can formulate my dual objective function in terms of what I have from the primal case. So, let q of alpha be the dual objective function. So, this q of alpha is basically summation I equals 1 to n alpha I minus 1 half summation I equals 1 to n j equals 1 to n alpha I alpha j di dj xi transposed xj. So, this is my setup. So, it is interesting to note, while in the primal problem the Lagrangian was dependent on the weight vector. We have eliminated this weight vector in terms of the Lagrange multipliers alpha I and the training samples xi di, right. Xi is a vector, di is the response which is +1 or -1, and given the training samples, that is xi di pairs I equals 1 to n, we are interested in arriving at Lagrange multipliers alpha I equals 1 to n, that maximizes q of alpha. Okay. What are the conditions? We have the same conditions. So, one is summation I equals 1 to n alpha I di equal to 0, because we are connecting alpha I and di. So, the other condition now is in terms of alpha i's, and alpha I is greater than or equal to 0 for every I equals 1 to n. Now, given the training data subject to these conditions, we want to optimize q of alpha, that is we want to maximize q of alpha subject to this subject to these conditions, and in that sense the dual problem is completely recast in terms of the training data. This is an important detail. While the first problem involved W, here it is in terms of the variables that are essentially the Lagrange multipliers. So, once you obtain the optimum Lagrange multipliers alpha optimum for every constraint I, right. So, I is every constraint, each constraint. Then we will compute the optimum weight vector. So, I will use the same notation OPT. Sometimes I may use just O or sometimes OPT. So, the reader can figure out this detail. So, the optimum weight is basically summation I equals 1 to n this Lagrange multiplier times di times xi, because I just plug in alpha OPT in condition 1. Remember this W was summation, W optimum is summation I equals 1 to n alpha I times di times xi, that is how I landed up. But since alpha i's can be optimized by solving the dual problem subject to the constraints, let me get alpha optimum for each constraint I. So, once I get that, I plug in those values to compute the optimum weight vector W given by this equation. So, from this I can compute my bias, B0 is 1 minus W transpose XS X of S, where D of S is essentially 1. So, this is sort of straightforward. Now, we have this optimum hyperplane for linearly separable patterns. So, we formulated the SVM so that we can solve for the optimum hyperplane, that is we want to get the right bias B0 and the weight vector W in terms of our training data, that is xi and di pairs, and we solved it, and this is for the situation where we have linear separability of patterns, right. When we do not have linear separability, then you cannot have a hyperplane that can separate the patterns completely with 0 error. There would be some error, because some points in class A will be lying in the decision boundary that corresponds to class B, class second class. So, you can have a situation where you can see this through the board. So, I can have this, assuming this is my hyperplane, I can have these x's and some x's are here, and I can have these circles and some circles could have been here. This could be a situation where it is non-separable. Okay. So, we will discuss this situation where we live with non-zero errors with our linear decision boundary, and that would be our discussion next.